Okay, I want to go through some classic limits. So the first one I want to talk about is the limit as theta goes to 0 of sine of theta over theta. So sine of theta over theta, if we were to directly substitute, we would have 0 over 0, which is an indeterminate form, meaning we don't know what the limit is, so we have to do something to it to find out. So I'm going to give you a trigonometry-based proof of what this limit is. So let's look at the unit circle. Okay, so here we've got a unit circle. Here's 0, here's pi over 2, here's the origin. I'm going to call this point here where the x-axis and the unit circle meet, I'm going to call that point A. I'm going to draw a line at some angle theta, okay? And so it's intersecting the unit circle, we'll say, at some point B. And then I'm going to go ahead and actually extend this line out and extend a line up from the point A. Okay. And the point where they meet, I'm going to call that D. And let's see, I'm also going to drop a perpendicular down from the point B to the x-axis. And where the x-axis meets that perpendicular, I'll call that C. Okay. So can you see three things here? One, we've got a smallish right triangle. We call it triangle BOC. We have a segment of a circle. I'm going to outline that in red. Okay, so we have a pizza-shaped segment of a circle. I'm going to call that segment BOA. And we have a very large, well, relatively large, right triangle here, DOA. Or I'm sorry, yeah, DOA. So in here. Okay, so there's the largest right triangle on the page. I'm calling that triangle DOA. Okay. Let me erase something here. Okay, so now that you see them all traced, hopefully you can all agree that the area of triangle BOC has to be less than this red sector of a circle, BOA, and that in turn has to be less than triangle DOA. Okay, so we're just thinking about the areas of these three objects. Hope you all agree. So the area of a triangle is 1/2 base times height. Let me just remind you of that. The area of a triangle is 1/2 base times height. And the area of a sector, okay, it may have been a little while since you've thought about the area of a sector. Hopefully you went over it in your last trig class, but the area of a sector can be found with the formula 1/2 r squared theta. Okay, so the area of triangle BOC is actually 1/2 times the base, which if you recognize this as a right triangle from the unit circle, the base here is just cosine theta, and the height is going to be sine theta. And that's less than the area of the sector BOA. Well, if we use the area of the sector formula, 1/2 r squared theta, r is 1 because we're talking about the unit circle here. So we would have 1/2 times 1 squared theta. And that in turn is less than the area of triangle DOA, which again we use the area of a triangle formula 1/2 base times height. So we'd have 1/2. The base of triangle DOA is 1, right? From the origin to the intersection point of the edge of the unit circle with the x-axis, it's got to be a length 1. And then the height, I'm going to leave that to you to convince yourself, but the height from this point A to point D is tangent theta. Okay. So how does this help us? Well, if I now divide each piece of the inequality by sine theta, oops, it's not right in here, and I simultaneously multiply everything by 2 to kind of clear the fractions, what do I end up with? Okay, well, if I divide by sine theta and multiply by 2, I end up with cosine of theta less than theta over sine theta less than 1 over cosine theta. And now I have theta over sine theta in the middle, so this is starting to look like we might be using the squeeze theorem, which we are going to. If I simply take the reciprocal of everything and flip the inequalities, I end up with this statement: 1 over cosine theta is greater than sine theta over theta is greater than cosine theta. And so I'm going to rewrite that kind of how we're used to seeing. I have an upper bound and a lower bound. We're assuming theta is somewhere between 0 and pi over 2. Okay, that's our assumption. So if I take the limit of the lower bound as theta goes to 0, I can use direct substitution. So if I evaluate cosine at 0, I get 1. If I evaluate 1 over cosine theta, the upper bound, okay, I'm taking the limit as theta goes to 0 there, I also get 1. So by the squeeze theorem, let me write that. Again, we always want to cite any theorems we use. By the squeeze theorem, and I'm going to have to go to the next page, the limit as theta goes to 0 of sine theta over theta is equal to 1. And that is a classic limit. Okay, this is something that you'll see come up over and over through the calc sequence. So I'd highly recommend memorizing this limit here. Okay. The proof is just something for fun. I wouldn't expect you to repeat the proof, but you know, it is trigonometry based. Hopefully you followed along. I would recommend going back through and convincing yourself that it's true. Okay, so the next kind of classic limit that I want to talk about is this guy right here. Limit theta goes to 0 of the cosine of theta minus 1 over theta. Okay, and for this one here, again, we can't directly substitute because we'll get a 0 over a 0. So here's where we might want to employ our nice technique of multiplying by a conjugate. Okay, if we do that, we're going to end up with limit as theta goes to 0 of cosine squared theta minus 1 over theta times cosine theta plus 1. And we can use the Pythagorean identity to rewrite the numerator as minus sine squared theta. Okay. And now we can kind of separate these two, well, we can basically separate this expression into two different expressions. So let me rewrite that on the next page. Theta goes to 0. I can write it as a sine of theta over theta times minus sine theta over cosine of theta plus 1. And now notice that this first limit is equal to 1. We just proved that. The second limit, if you were to directly substitute, you would get 0 over 2, which is 0. So we end up with 1 times 0, which is 0. Okay, so that limit evaluates to 0. So both the limits in this video here are classic limits. I would really encourage you to be familiar with them.